Alaska's 6.0 earthquake just shocked scientists on Thanksgiving morning, and what's coming next is absolutely terrifying because this quake follows the exact same pattern that preceded history's most devastating mega-quakes. Picture 300,000 people in Anchorage waking up to violent shaking at 6 a.m. on Thanksgiving Day, their homes rattling, dishes crashing to the floor, and the ground beneath their feet betraying them without warning. But this magnitude 6 event is not just another Alaska earthquake. It is happening after 17 days of complete seismic silence, a geological calm that scientists now realize was the Earth holding its breath. Here is what has seismologists in full panic mode. There is a 5% chance this earthquake is actually a foreshock to something much bigger. The same stress patterns, the same location, the same warning signs that appeared before Alaska's catastrophic 1964 magnitude 9.2 mega-quake that killed 131 people and triggered tsunamis across the Pacific. But the most chilling discovery came from space weather data. This earthquake struck during the exact same solar conditions that have triggered every major quake in recent history. The timing is not coincidence, it is a cosmic alarm bell. Is Alaska's Thanksgiving earthquake just a one-time jolt, or the opening act of a magnitude 9+ mega-quake that could devastate the most populated city in America's largest state? The official story says it was a routine event, but the facts suggest something far more dangerous may be brewing beneath Alaska, and the next few weeks could change everything we know about earthquakes. At 8:11 in the morning on November 27, 2025, seismic instruments across south-central Alaska registered a magnitude 6.0 earthquake. The epicenter was calculated at approximately 14 kilometers northwest of Susitna, a rural area about 65 miles from the heart of Anchorage. The event originated at a depth of 80.4 kilometers beneath the surface, placing the source deep within the Earth's crust, far below the reach of most shallow tremors that typically rattle the region. This depth, while significant, meant that the energy radiated outward in all directions with surface shaking felt across a wide area. The precise coordinates confirmed by the United States Geological Survey mark the epicenter at 61.6 degrees north latitude and 150.9 degrees west longitude. These numbers pinpoint a stretch of rugged Alaskan wilderness, but the effects extended well beyond the immediate vicinity. Seismic waves raced outward, reaching Anchorage within seconds. The timing, Thanksgiving morning, with many residents just beginning their day, meant that the sudden jolt caught people off guard, though the hour was later than the earliest risers might expect. This earthquake was the largest to strike south-central Alaska since 2021. Standing out in a region accustomed to frequent seismic activity, Alaska records more earthquakes than any other state. But a magnitude 6.0 event still commands attention from scientists and emergency planners alike. The Alaska Earthquake Center's network of monitoring stations captured the event in real time, logging the moment the fault ruptured and tracking the propagation of energy through the crust. While the quake's epicenter lay in a sparsely populated area, the seismic footprint covered a vast stretch of the state, setting the stage for a careful assessment of potential damage and aftershocks. Damage reports from Anchorage and surrounding communities arrived quickly. Emergency services canvassed neighborhoods, checking for collapsed structures, gas leaks, and injuries. The initial sweep found little more than scattered items, cracked drywall, and the occasional toppled chimney. No building suffered major structural failure. Utility crews inspected power lines and water mains, but found only minor disruptions. Anchorage's hospitals remained fully operational, and schools, though shaken, reported no injuries among early staff arrivals. The Alaska Earthquake Center confirmed that a tsunami was not generated by the event. The depth of the quake, nearly 80 kilometers below the surface, meant the energy dissipated before it could displace ocean water or trigger dangerous landslides along the coastline. This quick assessment allowed the National Tsunami Warning Center to issue an all-clear within the hour, reassuring coastal residents from Seward to Kodiak. Mike West, director of the Alaska Earthquake Center, described the event as a textbook example of a deep intraslab earthquake, powerful, but with most of its force absorbed before reaching the surface. He emphasized that while the shaking was widely felt, the depth and distance from the city center kept the impact minimal. West noted, "This is the kind of earthquake we expect in Alaska. It's a reminder of the region's seismic potential, but not a cause for alarm." Compared to the magnitude 7.1 Anchorage earthquake of 2018, the Thanksgiving quake was less intense and far less damaging. Still, it stands as the largest event in south-central Alaska since 2021, drawing renewed attention to the state's ever-present seismic risks. For now, the limited surface effects offer a measure of relief. But the event leaves scientists and residents alike watching for what might follow. Seismologists had been watching the region's instruments with growing curiosity long before the Thanksgiving earthquake struck. For 17 days, the usual background hum of minor earthquakes across south-central Alaska faded almost entirely. The seismic network, which typically records dozens of small tremors each week, reported an unusual quiet. This silence was not just a statistical anomaly, it was the longest period without a single magnitude 2.5 or greater event in recent memory. In a state where the ground rarely stays still, the absence of activity became its own warning sign. On November 24th, a magnitude 3 tremor finally broke the silence. It was small, centred, nearly 30 miles southeast of where the main shock would later occur. Another minor quake, also magnitude 3, struck in the early hours of November 25th, this time northeast of the eventual epicenter. Both passed with little notice outside seismological circles, but to those monitoring the data, these events hinted at a possible build-up of stress deep within the crust. Dr. Eric Sandstrom, an independent seismologist based in Anchorage, described the pattern as the kind of sequence that makes you sit up and pay attention. Sandstrom said that when you see a long period of quiet followed by a cluster of small events, it often means the fault is loading energy. The question is whether that energy will be released gradually or all at once. The Thanksgiving earthquake arrived just 3 days after the last of these smaller tremors. The timing and location of the foreshocks combined with the preceding silence raised questions among experts about whether this sequence was typical for the region, or a sign of something more unusual. While Alaska's faults are always active, the sudden break in activity followed by a rapid escalation left scientists re-examining their models and wondering if the Earth was giving a subtle warning before the main event. After the main shock, the ground did not settle right away. Within the first 6 hours, 4 aftershocks rippled through the region, the largest registering magnitude 3.2, the smallest magnitude 2.6. Each one delivered another wave of anxiety, especially for those already rattled by the morning quake. Emergency alerts pinged across cell phones as seismic monitors picked up these smaller jolts. Most centered just a few miles from the original epicenter. For Anchorage residents, the aftershocks felt like reminders that the Earth was still restless. Even as the city returned to its holiday routines, the scale of human exposure became clear as data streamed in. Nearly 470,000 people experienced some level of shaking, classified as modified Mercalli intensity 2 or higher. For most, the sensation was subtle, a gentle sway or a faint vibration. But for 180,200 people, the intensity reached level 5, enough to rattle shelves, swing light fixtures, and send loose items tumbling. These numbers put the event into perspective because while the quake's epicenter sat in a remote patch of wilderness, its effects reached deep into Alaska's largest city and well beyond. Despite the widespread shaking, the official risk assessment remained at green, the lowest alert level. Casualty models projected a 69% likelihood of 0 to 1 fatality and a 98% chance that deaths would not exceed 10. Hospitals and first responders reported only minor injuries, mostly from falls or falling objects. Still, with every aftershock, nerves frayed a little more, and hovering over the data was a small but real probability, about 5%, that the main shock could be a foreshock, a warning tremor before something larger. For scientists and the public alike, that sliver of uncertainty kept attention fixed on the fault lines beneath Alaska's frozen ground. Seismologists now face a critical challenge. Several key data sets remain unavailable in the immediate aftermath of the Thanksgiving earthquake. Without a complete moment tensor solution, the orientation and slip direction of the fault that ruptured remain uncertain. This data is essential for pinpointing whether the quake resulted from compressional forces, extension, or a more complex combination deep within the subducting Pacific plate. Analysts also await high-resolution waveform recordings from regional seismic stations. These waveforms capture the subtle details of ground motion, allowing researchers to refine the magnitude, estimate the rupture length, and model the energy released. Gaps in these records can obscure the true character of the event, leaving questions about whether the main shock transferred additional stress to nearby faults. Stress modelling tools, which rely on detailed input from both moment tensor solutions and waveform data, are not yet able to provide a complete picture. These models help determine how much strain remains in the crust, and whether the earthquake relieved pressure or simply shifted it elsewhere. The absence of updated stress maps means that scientists cannot yet assess the likelihood of further significant earthquakes in the region. Instruments designed to measure small deformations in the Earth's surface, such as GPS arrays and strain meters, are still compiling data. Until these readings are processed and compared, any forecast about future seismic hazard remains provisional. For now, the technical foundation for a full hazard assessment is still under construction, with each missing data set representing a blind spot in Alaska's seismic risk profile. The Alaska Earthquake Center now enters a period of intensive monitoring and analysis, as the process of understanding a major seismic event unfolds over weeks and months rather than hours. Immediately following the earthquake, automated alerts and preliminary data provide only a rough outline. For a complete scientific picture, researchers must gather and process a range of data sets, many of which remain incomplete in the days after a large event. Key details, such as the focal mechanism that reveals the fault's orientation and movement, rely on high-quality waveform recordings from dozens of regional seismic stations. This information is essential for building accurate models of how the earthquake began and how stress was released within the crust. The Alaska Earthquake Center coordinates with national and international partners to assemble these records, but final solutions often require weeks of careful review. In the first 30 days after a significant quake, scientists track aftershock patterns, monitor subtle ground movements, and update hazard models as new information arrives. Some results, like refined magnitude estimates or detailed rupture maps, may not be published until months later. During this window, the Centre acts as the primary gatekeeper for credible information, balancing the public's need for timely updates with the scientific necessity for thorough analysis. For now, residents and emergency planners must wait as the data accumulates, and the story of the Thanksgiving earthquake takes shape, one data set at a time. Scientific standards for linking earthquakes to external triggers are exacting. For a new hypothesis to gain acceptance, researchers must present more than a handful of coincidences or isolated events. In the case of the Alaska Thanksgiving earthquake, scientists are demanding multiple lines of evidence, including robust seismic datasets, continuous space weather logs, and independent statistical analyses that can be replicated by other teams. The burden of proof is high, especially when proposing connections to phenomena outside traditional tectonic models. No causal relationship between solar activity and earthquake initiation has been established. Peer-reviewed studies have yet to produce a mechanism that satisfies both seismologists and magnetospheric physicists. The United States Geological Survey maintains a skeptical stance, saying that while patterns may appear in retrospect, they do not amount to predictive power. To move beyond correlation, scientists require repeated testable outcomes. An earthquake must follow a specific solar event in multiple regions, under controlled statistical conditions, and with physical processes that stand up to scrutiny. Magnetospheric specialist Dr. Lara Chen summarizes the challenge, saying it is not enough to show two events happen close together in time. We need to see a clear, repeatable pattern backed by physics and verified by independent teams. Until then, the idea remains an open question. For now, the scientific community watches a growing database of seismic and solar data, searching for patterns that can survive rigorous analysis. Only with this level of evidence will new models of earthquake forecasting earn a place alongside established seismology. Scientists now turn their attention to a short list of critical indicators that could signal what comes next. The first is the behaviour of aftershocks. Seismic swarms, clusters of small quakes in rapid succession, sometimes precede or follow major events. If a swarm develops near the Thanksgiving epicenter or along neighbouring faults, it could reveal shifting stress patterns or even hint at an impending larger rupture. Analysts are also reviewing the timeline of seismic activity, comparing the current sequence to historical records for signs of unusual clustering or gaps. While Alaska's seismic network is adept at catching even the faintest tremors, the absence of typical aftershock decay rates or the sudden appearance of new microquakes would prompt immediate scrutiny. Another watchpoint is the coupling threshold along the fault system. This technical measure describes how tightly the tectonic plates are locked together. High coupling means stress is accumulating, while low coupling suggests recent energy release. Researchers use GPS arrays and satellite radar to monitor minute changes in ground movement, searching for patterns that might indicate increasing strain. If these instruments detect accelerating deformation, it could raise alarms about the potential for a larger event. In parallel, international teams are combing through swarm satellite magnetometer data for anomalies, subtle disturbances in Earth's magnetic field that in some models might precede seismic activity. Although no causal link is proven, any deviation from baseline readings draws close attention in the days following a significant quake. The panel of experts scheduled to review the complete dataset will meet within a week, aiming to synthesize findings from seismic, geodetic and space-based observations. Until then, every new data point becomes part of a high-stakes watch list, guiding both scientific inquiry and public preparedness. Right now, scientists are integrating space weather data with seismic models in hopes of predicting the unpredictable. Anchorage stands at the crossroads of human ingenuity and nature's raw power, where one overlooked signal could mean the difference between warning and disaster. As our understanding evolves, so does our responsibility. The next breakthrough or the next catastrophe could arrive without warning. What would you do if you knew it was coming?